Here we go. Hey, everybody. Welcome once again to Astronomy Daily Live. It's 2 hours UTC, and it's time again to gather around this group of friends in our sort of virtual porch here, sitting out on the back. Got our lounge chairs, right? Leaning back a little bit with our consumable of choice and spending the next little bit, maybe an hour or so, just thinking and talking astronomical thoughts. So yeah, hope everybody's doing well. It's been a little wet here today. The remnants of Hurricane Rosa are moving through, and as predicted, we're getting a little bit of rain. Most of the rain is to my west. So we're getting a little tiny bit, but it's nice. It's nice. And I see in the panel there, Bobby is here. What is going on?
Hey, nothing much.
All is well in your world?
Oh, yeah. All is well here.
Good. Very good. I noticed that Christian Reddy is now live streaming. He did his first live stream. He sort of did a test yesterday, to work through all the kinks. And today, I think he did his first official live stream. And his YouTube channel is called, let me get it here. Shoot.
I forgot it too.
Yeah, that's, this is Astronomy Daily Live, where nothing is really prepared until the moment it is thought of. So let me see if I can find him here really quick. Actually, I was just watching that, so it's probably in my history. So sorry, let me.
I was watching it live too. He's a good guy.
Yeah, it's called Launchpad Astronomy. Launchpad Astronomy, and I guess he's calling the live stream Launchpad Live, which I think that's a pretty catchy phrase. Yeah, so definitely check him out. He, from what I've seen so far, he really knows his stuff, and he's a. I'm not exactly sure what he does professionally in terms of research or anything, but I know that he is a teacher. I don't know where, somewhere on the East Coast.
He said he doesn't need moderators now, but maybe somewhere in the future he probably might need some.
Well, that is all of our hopes. So that moderators are needed and greatly appreciated. So yeah. Here's hoping that he is going to need some kind of help. I greatly appreciate the help I get. So I think that's great. So anyway, check him out, Launchpad Astronomy.
It's probably a bit messed up, and then watch that Q&A course by Tim Skull. If she still wanted a moderator, she should have counted me in on the first one.
Yeah. Well, you got to,
because she did have trolls, but she didn't have moderators.
Oh, wow. Yeah, you just have to keep on her because, I realized years ago that it's like, if you don't ask, then it's like, well, you're not going to get what you want. So you at least have to ask. And even if it's a no, then it's like, okay, it's a no. So yeah, I just started watching Christian Reddy's live stream. So not exactly sure where he went with his topic, but he was talking about Pluto and why it's currently not a planet. And yeah, I mean, I've talked about that here. At least my thoughts on that, and and I'll just reiterate them here shortly, and that is I don't really care if something is called a planet or not, because as far as I'm concerned, that's sort of just like I mean, we humans like to categorize things, um, and everything is so interesting and unique and incredible that I mean, everything is sort of in a category by itself, right? I mean, that goes for people, it goes for trees, it goes for even cars, right? That same make and model, same year, you know, um, this one was here on the assembly line, and that one was there, and they're always a little different, right?
Now, when
Um,
it comes to astronomy content, and you got like some of these terms that you hear them now, do you think you would and Uncle Bill would make a better moderator than me when it comes to astronomy things?
no, I think you're doing great. The more the merrier. I think uh, for me, the more help I can get, I am.
Well, what I was talking about when Christian Brady's is becoming more popular, and he does too have the trolls.
Yeah, yeah. Well, as I said, here's hoping that we all get a certain amount of trolls, because that means that word is getting out, and that's a good thing, right? And so yeah, um, having moderators to uh,
Now, I have a question. Is it better moderators on your first stream, or how many streams you have to go in order to get moderators?
oh, I don't know. I'm no expert in this at all. I'm
I
you know
think what it is, if you're popular, but you never did a live, like let's say you're being popular, like maybe 2, 3, 4, 5, 6, 7 years, and you just started your live stream, I'd say get your moderators up and play now, so when there are trolls, they just be with a gun and stuff.
pow pow
The bam hammer
the
with
ban
my
hammer.
pump up kicks. You better run.
The blue crew with their wrenches. Wham!
Did you listen to that song? Bounce Boston People Pumped Up Kicks? I put it on the Discord.
Uh, you know what? I started to listen to it, and then for some reason I stopped, and I never got back to it. So I need to do that. I want to say hi to Tom and Crystal,
Yeah, let's get
both
spaced out, baby.
both in the chat. Let's get spaced out. Hey, I'm almost in a constant state of being spaced out. So you know, you're sort of seeing the norm here. so so yeah, but nice to see you both in the chat. Hope everything is well. So yeah, check out Christian Reddy, um, and I forget the name of it already. Launchpad Astronomy is his YouTube channel.
A weekly stream or a daily stream?
I'm not sure. I'm not sure. Did you watch the whole thing?
I got like, I know it was like about an hour and stuff. About 5 minutes before he closed out, I had to go to the store.
Gotcha. So I mean, I would think that maybe he would have mentioned that, but maybe he didn't. So maybe he's still trying to work all that out. Like I was saying, he's a college professor, as well as I think other things. Not quite sure. So yeah, he's got a schedule um, to keep in terms of that. But you know, he's a very very good speaker, and um, you know,
Tom and Scudder, he said that I don't think he doesn't think that moderators need to be subject matter experts. They are there to keep the chat within the guidelines of the streamer.
yeah, yeah. I think that sums it up for me too, right? I mean, you know,
So,
I
I'm
mean,
guessing like Tamara Scove, she's been doing some space weather observations, and
mhm.
she does her live streams now. She should have better work with moderators.
Yeah, I mean, she's pretty popular already. So like you said, yeah, yeah. I mean, I I would think that the trolls and the creeps would probably get in there pretty quickly, right? Because she's going to have a pretty good following. Do you know how many viewers she had during her live stream?
Oh, that I don't know. I don't know at all.
I mean, was it a couple of hundred or was it like five?
Well, the chat was very active, so I'm guessing like you could say like 100 plus or
Yeah.
greater
Okay.
than 100.
Well, my observation is that if you've got 100 plus, then you're probably going to have at least a troll or two from time to time. So
And that's why that usually that she shouldn't hire moderators.
yeah, yeah. I think I mean I think that's a good idea. So I mean she'll probably figure that out eventually. You know, maybe she
Yeah.
doesn't realize that she needs them.
Yeah, when we was talking about when Tamara Skull did her first live stream, and despite of her popularity, she got like literally trolled and stuff. And she
Oh,
didn't have she didn't know that she needed moderators and stuff. I told her that I could be her moderator too because I have moderator experience. If I could be a moderator for you and Jill's, I can be a moderator for everybody.
oh
Because
yeah.
like
Yeah.
I like Tom Van Scott said, you don't have to be a subject matter person.
Right.
Just make sure that you're right on the spot.
Yep. You gotta keep your eyes open for those green ugly trolls. Cool. Space TV. Nice to see you. Talking about Tamitha Skov's live stream.
Having a stove.
Yeah. Does she have a YouTube channel that you recall off the top of your head, Bobby?
Yeah, yeah, it goes by her name as well. She does like weekly
Is it?
or
Okay.
shorty soul reports.
Right. Yeah, but she's
The Space Weather Woman, they call her.
yeah, yeah, the space weather woman. Yeah, yeah. She's been around for quite a while too. So yeah, does really really well. Yeah, good stuff. Good stuff for
Now,
sure.
You love to do WWB with your applications, right?
That's how I usually do it. Yeah.
I had to do that to reset my weather radio because what happened about a couple of months back, a lightning struck down the transmitter.
Ooh.
And it took the station out of commission. They just repaired it, and now I'm just reprogrammed the weather radio.
Oh, cool. Cool. So you'll have that back. That'll be nice.
Mm-hmm.
Cool. All right. Let's see. So yeah, definitely check out Christian Reddy's YouTube channel over on. I'm gonna forget that every single time. Launchpad Astronomy, and his live stream is called Launchpad Live. So yeah, he just started on that. sounds like he's going to do a good job. So, but yeah, I don't know if it's going to be weekly or daily or monthly. I'm not exactly sure. He may still be, trying to figure all that out. So yeah. All right. Well, cool. Let's see. Just checking the chat here really quick.
Not much in the chat.
Not much. Not much. It's a nice quiet chat today. Don't mind that one bit. So I found a paper that just came out on Archive that sort of caught my eye. I'm not really that much into looking for the extrasolar planets, but it is a pretty intriguing technical thing, right? Because ultimately,
Did you direct me to Isaac Arthur according to Space TV?
I don't know.
I don't know. I don't know him either. Okay, one I put on the chat is like the call to listen numbers for WWB and WWBH. I just found like on the website and stuff.
Cool. Yeah.
So if you don't have a shortwave radio, you can use those numbers, and you can still do your applications and stuff.
Sweet. Yeah. So Isaac Arthur, definitely check him out.
And you want those numbers on the Discord too?
Which numbers?
For call to listen for WWB and WWBH.
If you want to, sure. That's cool. It's not quite astronomical, but close enough. So yeah, check out Isaac Arthur for sure. And yeah, he just started a live stream too. I noticed that he was trying to do one the other day, and yeah, I think I was watching it there, and it went off, and I don't know if it ever came back on. So yeah, we'll have to.
Hey, I put those numbers in the chat, and I'm about to put them on the Discord.
Cool.
Now,
thanks.
where do you want them at the Discord? Like on space stuff?
Yeah, that sounds like a good place. Yeah, that sounds all right. Anyway, so over on archive.org, I'm going to share my screen here. Found this pretty interesting new paper. Hide that. On the detectability of transiting planets orbiting white dwarfs using the Large Synoptic Survey Telescope. So the LSST is currently being built, right? So it's not built or running yet. So they're making some models and making some guesses. And I just found this a little bit intriguing, and I guess I hadn't really thought of it, I guess, but I didn't realize that it doesn't look like, at least from what I'm seeing here, and we can sort of dive into it a little bit more here, but it's sort of looking like no extrasolar transiting planets have been detected yet going around white dwarf stars. So
okay. Hey, what I did, I put the link on the Discord.
Okay, cool. Excelente. All right, cheers. I need some of this hydrogen hydroxide. Cheers.
And I got my water right here. Cheers.
All right.
Remember
to hydrate. It's the best thing in the world. The most incredible molecule ever. So yeah, I'm sort of intrigued by planets orbiting white dwarf stars. These white dwarf stars are pretty interesting objects, all by themselves, right? They're objects that are about the size of the Earth, but they have the mass of maybe half or up to one entire solar mass. So a huge amount of matter, a lot of mass, right? And there is a difference between matter and mass, but let's just talk about mass. Quite a bit of mass in a small amount of space makes for high densities. Just everything. Just very much more than what it normally is, right? The gravity is higher. The magnetic fields are very, very strong. That kind of environment, right, has just got to be super, super, super intense, right? And but here we are, looking at these things. And these are objects where they have compressed themselves down such that the only thing that is sort of holding them up is the pressure that is exerted by the electrons of these atoms pushing up against the electrons of these other atoms, right? So they're like extremely compact. And that's how, at least as the story goes, that's how these objects can be formed, because that amount of material is sort of squeezed down into this very, very, very dense, small ball of stuff, and you get a white dwarf. And these white dwarfs are, in theory, not really doing anything thermonuclear. I'm not exactly sure if that's sort of an observed, known fact, or if it's just sort of a guess. Because I think that there are some thoughts that they could be doing, some kind of thermonuclear stuff on the surface of these white dwarfs. But yeah, I don't know. So yeah, white dwarfs are pretty intense objects. Our sun, along with most of the stars in the sky, at least the theory is that most of those are actually going to become white dwarfs. And at least as the story goes, as the theory goes, these white dwarfs are not generating any of their own heat. They're just slowly dissipating heat. But it takes tens of billions of years for some of these white dwarfs to cool down. The temperature of sort of a typical white dwarf is around 20,000 degrees Kelvin. I think they go down to maybe 5,000 or 6,000 Kelvin, and maybe as high as 70, 80, maybe 100,000 Kelvin. So there's quite a range in temperatures, depending on lots of factors, right? Mass, environment, what the star was made of, all kinds of stuff, right? So yeah, these guys at Columbia University have made some guesses in terms of being able to detect planets going around these white dwarf stars. I think that's pretty interesting, pretty cool. And so let's let's see what they have to say here. This is a pretty short paper, 9 pages. Okay, it's not really long. It's not really short either. So let's see. Here's the abstract, which is sort of like a summary of the entire paper, right? In sort of one paragraph. No extreme details here. Just sort of, this is what we're trying to do, and this is how we did it, and these are the results. Blam. And then the rest of the paper, of course, gets into the details. So white dwarfs are one of the few types of stellar objects for which we know almost nothing about the possible existence of companion planets. So let's see, they're looking around, and I guess they're finding metal contaminated atmospheres and circumstellar disks and planetary debris. Huh, okay. Never heard of that. Yeah, and as they say here, the challenge for looking for transits of white dwarf stars is that white dwarfs are intrinsically very, very faint because they're so small, right? I mean, they are literally the size of the Earth. And, it's amazing that we can see them at all because, right? I mean, a normal Earth, right? Can't see that at all, right? I mean, if there are Earths out there right now, just sort of floating around in space, they're too small to see, right? But these white dwarf stars are so incredibly bright that, even though they are small, we can still see them. So, but what makes it really, really interesting, right, is that because they're so small, there's if a transit is going to happen, then it's probably going to be a deeper transit, meaning that, when we're looking at the light from the white dwarf, and say it's the size of the Earth, okay? Well, say that a Jupiter-sized planet passes, right in front of it from our point of view. Well, sort of depending on distances and all that kind of stuff, that large planet, right, is probably going to block a large majority of that star, right? Because their apparent size, or at least the apparent size of the transiting planet, might even be larger than the apparent size of the white dwarf star. And therefore, when a transit takes place, all of the light from that white dwarf is going to be blocked out. And I'm surprised that we haven't seen anything like that already. That seems really, really likely. So let's see. The LSST is I can't even fathom what the LSST is going to reveal to us, because we're finally I've been waiting for this for my entire professional life, right? And that is to get into the time domain of this astronomical stuff, right? Instead of just looking at pictures and looking at spectra and all that, I've always been interested in seeing how things change and what kinds of transient events, are going on, right? I mean,
Tell me this is actually true. Scientific papers where you expect spoilers on the first page, said Uncle Bill Duran.
yeah, yeah, that's exactly what this is, right? The abstract is the spoiler, right? I mean, you can read this, right? Read the abstract, and I mean, you can more or less get it all, right? I mean, there's a lot of details that are left out, but there isn't anything, that is like, untrue or glossed over or ignored or anything, right? I mean, it's all there. So yeah, the abstract is a spoiler. Yeah, for sure, for sure. So yeah, um,
For those of that
LSST.
never read a scientific paper before, is it better if you read the whole thing and not just the abstract?
Well, my recommendation is always this, right? If you're just getting into reading these, right, what you should do first is look at the title. And if the title, sounds interesting, then you can go a little bit further, right? And that further is definitely looking at the abstract. And if the abstract sounds enticing, then, either dive in, right, like this, or what I like to do is I like to look for the pictures. The pictures and the charts and the tables and all of that. Especially if you're new into all of this, that's a good place to start, at least. But yeah, I mean, once you read the abstract and it sounds interesting, it's like, okay, well, I want to find out, a little bit more. What did these people do? How they do it? In this case, they're setting up some kind of simulation. So it's like, okay, what's the simulation they set up? What kind of parameters were they able to, mess around with? And then what are the results? Right. So yeah, I always like to go for, pictures first, and yeah, there's a few here. So yeah, we'll get into these a little bit more. Oh, these seem a little weird looking, but yeah. Viva C. Okay, so yeah, as most of these kinds of papers go, there's usually an introduction that sort of lays out what the problem is and what's been done in the past, and then sort of a thing saying, okay, well, this is what we're going to do, right? So let's see. Vast majority of stars end their lives as white dwarfs. Yeah, so there's a collapse. As a result, these remnants have radii similar to that of the Earth, but with a mass, typically half of that of the Sun. But yeah, they are thermally cooling down, right? So they're extremely hot, right? Like I said, I think typically they're around 15 or 20,000 degrees Kelvin, and they're just radiating, right? So that takes a really long time. So let's see. So yeah, they're just talking here about exoplanet detections, looking at these things called FGK stars, which is just the spectral type, right? An F star, a G star, and a K star. Our sun is a G2. I think it's a G2. So these are just, similar types of stars to our sun. Because, right, and as they say here, the basic argument was that these kinds of stars, FKG stars, FGK stars, we have an example, right, of a G star that does have a, very, very, very Earth-like planet, specifically the Earth itself. And so, yeah, that's a good place to start, right? If you find a even more specifically, right? I mean, if you find another G2 star, then it's like, well, we know for a fact that a G2 star can support a planet with life, right? So let's go out and find all the G2 stars and see what is going on there, right? So, and they sort of, spread that out a little bit because, I mean, there probably are, I would think, quite a few specifically G2 stars, but they spread it out a little bit and said, okay, let's look at F stars and G stars and K stars because they're all sort of similar, right? But then I think it was Kepler, right, that started detecting transits around M dwarf stars. So these are much smaller stars, much cooler than the sun, but seem to also be able to, at least support planets, right? We don't know about life on those, but at least seeing what they think are planets transiting these M dwarf stars. So at this point, right, you have to say, okay, well, we found some stars or some planets that are transiting solar type stars. Well, now we're finding transiting planets going around M dwarf stars, and that sort of opens up the possibility that maybe we should be looking at all the stars out there and seeing what's going on. So yeah, this is just an attempt to start including white dwarf stars. I don't know why you couldn't start observing white dwarf stars now. Don't know. And I guess I'm a little surprised that Kepler hasn't. I don't know. I mean, they are pretty faint, and Kepler, I don't know what the limiting magnitude of Kepler is. I wonder if we can find that out. I'm going to check the chat really quick. Oh, there's a bunch going on here. They're going 5 minutes later. Cool world, scientific papers. Okay, cool. So right, I'm caught up there. So I'm wondering if we can find out easily what the limiting magnitude of the Kepler spacecraft is. As you can see, I was over on Cal Sky before we got on here, but I'm going to Kepler spacecraft. Kepler spacecraft. See if we can just find out any info about how faint this thing goes. Wow, I didn't realize that the Kepler telescope was almost a meter in diameter. Really? Wow. I thought it was much
How
smaller.
old is the Kepler compared to the Hubble?
I think Kepler, let's see. It says here that Kepler started service on May 12th, 2009, and the HST was initially launched in 1990. So Kepler is 19 years younger than HST. But let's see. I'm trying to see if we can. Let me just. Oh, did I have it there? Performance. In terms of photometric performance, Kepler has worked well, much better than any Earth-bound telescope, but short of design goals. The objective was a combined differential photometric precision of 20 parts per million. 20 parts per million is 20 divided by a million times.
Now, Uncle Bill, the white dwarfs are any fainter than the red dwarfs we have in observing, and maybe a little less common.
Well, you know, white dwarfs are only called white dwarfs because they're small, right? I mean, white dwarfs technically aren't stars, right? I mean, one of the things that makes a star is that it is at least as the theory goes, it's going through some kind of nuclear fusion, right? And white dwarfs, that's not the case. As I said, I'm thinking that we're pretty sure that maybe thermonuclear events are happening on the surfaces of white dwarfs, but not in their cores. I could be wrong about that, but yeah, I mean, a white dwarf is sort of in a category by itself. I mean, I have a hard time calling it a star. Now, I mean, that opinion could be modified, but anyway, having said that, I'm thinking that white dwarfs. Yeah, you know, that's a good question, Uncle Bill. I'm not exactly sure, because I'm sort of thinking that there's quite a bit of both of those, and I don't know if there's one that's more common than the other. Don't know about that. But as I said, you know, the population of white dwarfs is the result of stars evolving, right? Going through their lives and ending up this way. Red dwarfs, on the other hand, are formed stars. They're still, you know, either early in their life or midlife, and because they have such low mass, they just burn through their fuel really slowly, relatively speaking. So yeah. I think, you know, calling a white dwarf a star, technically, I guess I'm going to have a problem with that. Although I do that. Yeah, I mean, I call it a star, but technically it really isn't. It's a electron degenerate object. It's being held up by the electron pressure of the atoms, and that's it. A neutron star, right, is a neutron degenerate object, and that's when the core collapses so tightly that the electrons in their um, orbits around the nuclei of atoms actually get squeezed together, right? So the protons and electrons actually merge, and so you just have this object, which is just, at least according to the theory, right, mostly neutrons. Hence the name neutron star. But again, star, I think, is not technically an accurate term. So yeah. Anyway, let's see here.
Now,
So
is it more of a theory that we can see more new elements on these stars, or no?
are you talking about white dwarf stars?
I'm talking about when the star, like Carl Sagan in episode 9 says that when a star explodes, it sends like the elements they synthesize into interstellar space. So I was wondering, are we going to be seeing new natural elements real soon?
Yeah, as the theory goes, right? I mean, what happens in the core collapse that results in a neutron star is that the core of these stars collapse, and that creates a huge shock wave, right? I mean, it collapses, and then it sort of does a bounce, right? It goes boing, and that shock wave outward blows all this stuff out into the interstellar space, and all of that stuff, obviously is going to be the atmosphere of the star that was there, but also quite a bit of material is going to be blown off of the neutron star too, right? I mean, as the theory goes, it isn't a perfect collapse. It's non-symmetric, complicated, right? Really complicated. We were actually looking at a paper that Adam Burrows did about the first, I forget how many fractions of a second after a supernova explosion. Well, that's what that explosion is that shock wave after this core of the star collapses. At that collapse, all kinds of stuff happens, right? New elements are created, and then as a result of the explosion, those new elements get blown out into space, and yeah. So, but no, Bobby, I think my guess is that if there are any atoms, right, created that have that have an atomic number larger than 92, then they're going to decay. So my guess is, and we could probably look and see if this is true or not, but my guess is that quite a few elements are created with an atomic number greater than 92, and we may be able to observe those, but they don't last very long, right? Because they're not stable. So the only ones that are stable to a certain extent are the ones that go up to 92. And even some of those, right, aren't incredibly stable. So yeah. As the theory goes, all the elements heavier than iron are created inside of supernova explosions. So yeah, kind of interesting. Let's see. All right, so back to Kepler, trying to see if we can figure out how faint these things can can go. So the objective was to have a very, very tight precision, right? 20 parts per million is 0.002% precision. So that's amazing. On a magnitude 12 star for a 6.5 hour integration. Yeah, that is tough. Allowing to, but yeah, that's not really saying anything about what the magnitude is supposed to be. So let's keep going here.
Now, if there's a possibility that Kepler will look at other solar systems in the Milky Way, or what?
Oh, it is. It is. I mean, Kepler has discovered apparently like around 3,500 planets. So yeah, lots of solar systems. I think weren't they saying something like 1.5 planets per star at this point? So yeah, they're finding them. So Kepler was designed to be sensitive to wavelengths between 400 and 865 nanometers, where the brightness of those stars peaks. Most of the stars observed by Kepler have an apparent visual magnitude between 14 and 16. But the brightest stars have been 8. Cool. Okay, so they're seeing pretty faint stars. Okay, and the reason why I wanted to bring that up is because there are quite a few white dwarf stars that are definitely brighter than 16th. Right? Oh man, there's got to be at least a few hundred that we know of, and now that we have Gaia, right? We have the Gaia database. We can look for white dwarfs in there because their colors are they sort of stand out, right? They're not a main sequence star, so their colors are completely different, right? So yeah, relatively easy to pick out from like Gaia. And then just have Kepler look at them all, because Gaia has measured their brightnesses too, and so if Kepler can see down to 16th, then yeah, I think it has access to, I would say, at least several hundred white dwarfs, and that's Kepler, right? What this paper is talking about is LSST. Right, and LSST can see much fainter because it's huge, right? It's absolutely huge. It's a huge scope. It's wow. I don't remember exactly, but it's big. I mean, it's a huge light bucket, so it can see to much fainter than 16th. I think it can see. I'm not sure. It depends on the exposure time, of course, but yeah, I would imagine that it could see pretty darn faint with a pretty short exposure. So yeah, see, here it is, right? With a radius of about 10 times less than that of the smallest M dwarf, a white dwarf star therefore provides what they're calling a major amplification of transit signals. And that's because these white dwarf stars are so small that it doesn't take that large of a planet to like completely block their light, which is why I'm sort of surprised that no one's ever seen these yet. I guess maybe we can look here and see if they have an estimate in terms of how long the transits are supposed to last, right? I mean, if a transit lasts,
will do the job with the whole. They will do the whole sky, but he thought that Kepler didn't have much life left in it anyway. And hey, Herpy Eater.
Herpy Eater. Hey there. Nice to see you in the chat. I like that name. Or is that Herp Eater? Herp Eater? Cool. Neutron stars, I mean, space TV, yeah, I mean, you can consider those dead stars, but I would also characterize white dwarfs as dead stars. Those, at least, you know, according to our theories right now, right, a star will end its life in one of three ways. And it will get to one of those three ways depending on what its mass is, right? What its mass is when it turns on, when it's born, how big it is, right? So any star that is about 1.4 solar masses or less, right? And I don't know how far that goes down. There might be a lower limit, not quite sure, but any star 1.4 solar masses or less will very, very likely become a white dwarf star. Okay? Any star that is about 1.4 solar masses up to I think they're saying maybe like 3 or 4 solar masses, and maybe even a little bit more, 5, 6, are going to turn into neutron stars. They're going to go through some kind of a supernova event and end up as a neutron star. And then any star that is more massive than about 6, 7, 8, 10, you know, on and on, at least according to the math, right, these stars will become black holes. So yeah, just to talk about Kepler here too a little bit. Yeah, Kepler is running out of fuel, as far as I know. I think it's supposed to. I think the end of the mission is December, right? Is that true? Are they going to turn it off? Don't remember exactly. But yeah, TESS, of course, is coming online now, and is definitely going to, you know, carry on what Kepler started.
If I recall correctly, TESS has been doing a great job too.
TESS so far has, I don't know if they've discovered 2 new planets or they've just detected 2 planets. So yeah, I'm don't recall if they found some new ones or if they just detected some old ones. But TESS is already doing its thing. Yeah, and TESS, I mean, that is such a huge amount of data as well. It's just absolutely crazy. Let's see. Okay, so the potential value of white dwarf exoplanet survey was highlighted by Egal, who argued that at least a few thousand white dwarfs would need to be surveyed to place meaningful constraints on the existence of planets around.
Yeah, it's burning real fast to compensate for the failed reaction wheels.
Yeah. Yep. Cool. Let's see. So, yeah, at least according to this guy, they're going to have to look at a few thousand. Okay. I'd like to understand his argument,
In space
his or her.
TV, there are only two types of death stars?
I guess technically, yeah. I mean, if you want to call a, you know, so-called black hole as one of the end lives of a star, I don't think that we really understand black holes yet. It's those are very much a mystery, but at least according to the math, right? Once you exceed a certain mass of a star, then it's just going to collapse and keep going, right? It never stops. So, and that is sort of, the definition of a black hole. So who knows? Who knows? Anyway, this guy is saying that they're going to have to look at a few thousand in order to place any kind of meaningful constraints on the existence of planets. And I, now, not having read this paper, which I could certainly do, right? I'm not quite sure why you would need a few thousand. I mean, I guess in order to put some constraints on things, maybe, but in order to make a detection, it's like you just need one. So, pretty interesting, though. Okay, so there have been surveys of white dwarfs for transiting planets, but wow, so they found no examples in 1,148 white dwarfs observed by Kepler. So that's kind of interesting, right? No transits, no planet transits amongst 1,000.
It's not possible for black holes to skip the star step, right?
At least according to the theory, Space TV, that is correct. Black holes are, like I said, one of the three end states of a star. And there they are, right? White dwarfs, neutron, and black holes. And we've directly observed two of these, right? And have indications of something that we're sort of calling a black hole. Yeah. So this is kind of interesting, right? That they've looked at all these white dwarfs and not found a single transit event. So then, of course, they go into, since a white dwarf is an evolved star, right? Then I mean, sometime in the past, even if there were planets, right, the star giant phase, very, very unstable, which probably isn't very healthy for planets.
There are theories that could be primordial black holes from the earliest parts of the universe, if he recalls correctly, Uncle Bill.
Yeah. Like I said, I'm from a very, very early age, the concept of a black hole was sort of a red flag in my head, and they still are. And I haven't heard about any black holes being created in a lab. I think there was some concern. I don't know how much it got into the scientific community, but there was some concern with the Large Hadron Collider, that the energies being used had had the potential of creating these so-called mini black holes. I guess nothing happened, right? So, yeah. But as far as I know, I don't think anything like that has been done yet. Not that I'm aware of. Not that I'm aware of.
If they were able to create a black hole, what would they see?
That's a very good question. I have absolutely no answer for that at all, because yeah, the only thing that we can see is sort of the effects of a black hole, right? Yeah, I mean, technically speaking, we shouldn't be able to see a black hole, just the effects of a black hole. So yeah, I don't know. If we were able to create one in the lab, it probably wouldn't last long, right? Because it's very, very small mass. Low energy, relatively speaking. But yeah, I don't know. Don't know.
If we was able to travel to a black hole, what would we really will see?
I also don't know that either, right? There's a location in the proximity of a black hole that's called the event horizon, and that's if you go inward of that, then apparently all the physics breaks down, and we have this weird situation, right? But if you're relatively close to it, technically speaking, because of its mass, you could, actually orbit it and not have any kind of problem at all. And actually, this is going back a couple days to a space movie that I forgot about until now. Who has seen The Black Hole? And who liked it? You ever seen that one, Bobby?
Probably not.
I highly recommend it. Highly recommend. It's awesome. And I think I'm pretty sure it's called The Black Hole. Pretty sure. But yeah, good movie. And yeah, for a while there was a space station, orbiting that black hole. So, okay, well, here we go. Let's keep going here. So yeah, because these white dwarf stars are evolved stars, maybe they've destroyed all their planets. But maybe not, right? Because they're seeing contamination in the atmospheres. They're seeing debris disks around white dwarf stars. And at least according to these guys, there is direct evidence of a likely disintegrating planet orbiting this white dwarf. So that's kind of interesting. Let's see. So there are two significant obstacles that face.
Stephen Hawking was right. When you create a micro-sized black hole, you should be blasted with Hawking radiation as the evaporates almost instantly.
Yeah. I don't. At least according to the theories, I don't think that those things last very long. And yeah, I'm not quite sure. If Hawking radiation is dangerous. If it is, how long of an exposure do you need? Yeah, I don't know. Let's see. So, two significant obstacles. in trying to find planets transiting white dwarfs. White dwarfs are faint. Okay, so yeah, because they're faint, right? They have to look at a lot of them, and they have to do relatively long exposures, and the transits last for minutes. Okay, that's something I didn't know. So meaning that, of course, the exposure times can't exceed that, because otherwise you're not going to see the transit, right? I mean, if you do an exposure, 5-minute exposure of a white dwarf star, right? When it turns itself off for 2 minutes.
Okay. Space TV, black hole and made in the lab shows signs of important entanglement. Article on New Scientist. And Uncle Bill, and he remembers the book and the movie called Black Hole. The book was fun, the movie was horrid.
Oh, okay, yeah, I don't know if that's the same one I'm talking about or not, Uncle Bill. I'm talking about the one with Anthony Perkins, and there's a bunch of robots, and they actually end up traveling through this black hole, right? So I think it was called The Black Hole, and I almost want to say that it was produced by Disney, I think. And I thought the movie was pretty good. I don't remember if there was a book or not. So I'm wondering if we're talking about the same thing. Okay, so you didn't like the movie? Okay, I did. I mean, it's not great, but I thought it was interesting enough. Yeah. But yeah, I didn't know that there was a book. Okay, I'll have to try to remember to check that out. Definitely. Let's see. So the LSST can observe down to 24th magnitude. I assume that is like with less than a 2-minute exposure. So down to 24th magnitude, they're expecting to see or have access to 10 million white dwarf stars. Wow. Okay, so they're going to be taking 2 15-second exposures. Okay, so that is definitely possible then, right, to see those kinds of transits. Let's see. So the most obvious drawback in using the LSST for this purpose of it is that it does not survey each patch of sky for long periods of time. Right. It just takes a shot and moves on. So, well, kind of interesting. That's a nice introduction for searching for white dwarf transiting planets. What's this? Okay, cool. Well, maybe we should continue looking at this tomorrow because, yeah, there's obviously, there's lots that can be talked about here. The LSST itself is like I said, it is. I think that's going to be a game changer for a lot of astronomy. yeah, I think it's going to be absolutely incredible. And I think we're going to get a taste of that with TESS for sure. I'm really, really anxious. I need to go and look if the test data uh, um, is available yet. That might be interesting to look at, because there's so much more that can be done with that data besides looking for transiting planets, right? I mean, you've got all these images, right? So okay, well, yeah, maybe we'll continue to look at this at another time. Just sort of, okay, so they're looking at the number of white dwarfs, sort of like a density plot of white dwarfs. So that's kind of interesting. These regions here are along the galactic plane. So there's so many stars there. It's like there's almost no point in looking, right? Because there's just too many stars. It's too dense. You can't really differentiate one from the other, right? Because they're so close to one another. So they look, where the Milky Way isn't. And as you can see, it's already starting, to rise here, the number of white dwarfs. So kind of cool. Yeah, I shouldn't get into this too much because then we'll get stuck. But there's some light curves. Cool. Yeah, let's we should take a look at this a little bit more. Maybe tomorrow. As I said, this looks pretty interesting, and it's sort of an intriguing idea. And I think what grabs me the most, I'm gonna stop sharing my screen. I think what sort of intrigues me the most about that, and actually let me let's see. The article title is above. Black hole made in the lab shows signs of quantum entanglement. Let's. I'm going to. Well, I'm going to see if we can get that. See that one. There's only one way to study a black hole up close. Build a copy in the lab. One physicist claims his desktop black hole, which swallows sound instead of light, has been spotted emitting entangled quantum particles. Huh. Interesting. In Haifa claims that he's seen Hawking radiation from his sonic black hole. So calling it a sonic black hole. Sonic black hole using a quantum state of a supercold fluid, right, called a Bose-Einstein condensate. I'll have to look at this a little bit more. Sounds a little bit interesting. I'm into sound anyway, so yeah, this idea of a sonic black hole is kind of intriguing as well. It constantly blows my mind. Oh, and what I'm going to do is I'm going to copy that link to the chat. There we go. And in fact, I'll put it over here on the Discord as well. I'll put it under science. I'll put it under the science channel. Here we go. All right. Well, like I said, there's way too many interesting things out there. And now, what's intriguing me about this white dwarf thing is that they haven't seen any planet transits around white dwarfs, and that's kind of puzzling, because you would think that there would be a pretty good chance of doing that. So, but they haven't seen any yet. So, interesting. I think we're going to have to continue looking at this paper, and I definitely will for sure. So, for now, cheers, everyone. And I think it's time to get on out of here. It's definitely past the hour. It's actually 3 hours and 21 minutes UTC. So yeah, I think we're a little bit past. So I think I'm going to let you all go for today. So thanks again so much for coming in and listening to me blab about all things astronomical. And I like to go off on the tangents too. So that matches personality really, really well. Just going off on all kinds of directions. I just have to pull us in occasionally, but that's easy to do here, right? Because we are casual and fun, and just having a great time thinking and talking all things astronomical. So it's always great fun. And you know what? Let's do this again soon. How about in about 22 and a half hours? Is that a good time? Good.
Sounds like a plan.
Sounds like a plan. Okay, I'm going to check the chat again really, really quick just to make sure that I am up to date. All right, everybody. Well, as I said, thanks for coming in. If you haven't subscribed yet, make sure to do so. Smash the thumbs up or the thumbs down, whichever you prefer. You could make some comments and spread the word, right? Spread the word. We are trying to find our people, right? I'm not trying to cast a huge net and sort of, catch people, when they're not looking or anything. I want this group to be the kind of group that really wants to sort of get into these kinds of things. Have fun, be serious, but have a lot of fun, right? Because I mean, all this stuff is just absolutely amazing and mind blowing, right? So okay, I'm gonna get out of here. Yes, I am getting the word that I have to get off of this round weird planet. It's just too much. So all right, take care, everybody, and I will see you all on the spin. Take care. Bye.
Later.